My today's topic is introduction to flood modeling, and today we'll be discussing these things. That is overview of the topic. So, what's flood modeling? So, what are the fundamentals or the basics in the field? Then, how did this field evolve? Then, what is the state of the art technology that is used in flood modeling? Then we'll go across two case studies. Then to get into flood modeling, so what should be your career path and what are the job opportunities in this field? So we'll be discussing this throughout our webinar. Then yes, so starting from our first content, that is overview of the topic. So flood modeling falls under disaster management. So yes, I mean the recent being the Uttarakhand glacier flooding, and yes, so there are various floods every year in India as well as abroad, and billions of money are wasted in, I mean, for not doing flood modeling. At least India, there are less flood modeling that is done in India, but yes, I mean we can avoid this. Then climate change. So whenever I do flood modeling, we usually apply climate change factor. Now this climate change factor is given by the hydrologists or by the researchers who work in the field, but as a flood modeler, we directly apply a percentage of it. Then infrastructure projects. So flood modeling is required in infrastructure projects whenever you want to build a bridge, I mean a new bridge, or if you want to see the impact of the existing bridge, or if you want to build a dam. So that are infrastructure projects. Then modeling and mapping. So yes, maps are produced and models are made to do this. Then fundamentals in the field. So you guys should have studied fluid mechanics in your second year, then environment and water resource engineering. So these are the crux which are required to build castles in flood modeling. Then you should be very well aware of hydraulic and hydrologic equations. So in hydraulic equations, I would say that you should know what's continuity equation, that is q is equal to av, and I mean Newton's second law of motion, that is what we also call it as a momentum equation, which is f is equal to ma, that is force into mass into acceleration. So in flood modeling, forces are pressure force, frictional force, gravity force. So I think, as the name suggests, these are easy to understand. Then mass comes into picture when you have rho. Then A is your local and convective acceleration. So what I mean by local is change of velocity in time, and convective is change in velocity of over position. So these are the two basic hydraulic equations which were developed by Navier-Stokes. So yes, so we call them as Navier-Stokes equation. And when these equations are reduced to 1D or 2D, we call them as set. So people should really get to know this, what these equations are. Then other than that, so in flood modeling, we come across various structures like bridges, orifices. Then there are several weirs, culverts. So I would recommend that people should have a good knowledge of these equations. So these are, I mean, these equations are developed using continuity equation. So people should really understand what happens when something happens, like q is equal to e. So what if my v get reduced? So what will affect to my cross-sectional area or to my floodplain? So people should have a good understanding of these hydraulic equations. Then people should really understand what is hydrology, because it's hydrology first and then hydraulic second. So people should know what's runoff. So runoff is equal to rainfall minus losses, and rainfall is just straightforward, that is the precipitation. and losses are nothing but your evaporation, evapotranspiration, and your infiltration losses that you guys usually study in your water resources engineering. So this is nothing but open channel hydraulics. So yes, so I would also suggest that people should know what is open channel. I mean, the things which I had described earlier. Then they should also have good knowledge of their catchment, because they should really understand when a drop of water will fall on ground. So how will it flow? So as I said, like, people should know what is their catchment, what will happen when the drop of rain will fall on ground. Then okay, this flow hydrographs are applied to our code area or our area of interest, and that is where our hydraulic model starts. So yes, so these are the basic fundamentals in flood modeling that people should be aware of. Then again, GIS and remote sensing. So I'll more or less focus on GIS, because whenever I start my day, I open my GIS and work on that, because models are built when you have a good understanding of GIS, then your projection system, then what is your DTM, then they should understand what's the difference between raster, vector, then what are the sources from where ground model can be downloaded, because there are few countries which allow free download of the data like rainfall or ground models. So yes, I mean, people should know what is GIS and remote sensing, because GIS is the foundation while building any hydraulic or hydrologic model. So GIS is also part of our model building exercises. Then yes, gravity and common sense, because unless and until you apply common sense, you'll not know how it will work, because it's not always that we can remember all those equations. So if we have a good understanding of gravity, so my drop of water will drop on ground, so in which direction it will flow. So if you understand gravity, then your life will become easy. And people should also know common sense, because what if I build a dam, so there will be impounding or a backwater effect will be generated if I build a dam. So people should understand these two things. That is why I have allocated this in fundamentals in the field. So how did this field evolve? We ask these questions to us, that am I at risk? So what is risk? So risk is nothing but probability into consequence, which we also called it as risk analysis. So it's also a part of flood modeling. I mean, this all these bullet points are part of flood modeling, so we'll just go through it one by one. So probability is nothing but your return period, which you study in your third year or final year. That is 2-year return period, 10-year, 100-year, 1000-year. And consequence is nothing but the damage. So that is why we say in terms of 0 to 1, if the risk is 0, so we say okay, we are at low risk. And if the risk is equal to 1, then okay, we say that we are at high risk. So this is risk analysis. Then what will happen if there is a development? So okay, so what if we have a new development? So what if we build new roads or bridges or culverts? Because there are various infrastructure projects going on in India as well as abroad or in the world. So we just add these structures in place and we see what's the impact. So we do the existing case and we do the proposed case. So existing is nothing but what it is right now, and proposed case is what will be after we build these roads, bridges, or culverts. And we do the difference between proposed minus existing, and that's our impact assessment. So this is also a part of our flood modeling. Then I think this is just straightforward. What if dam fails? So that is dam break analysis or dam breach analysis, and we produce reservoir fill map. What if my reservoir fails? So we produce maps for that. Then okay, so we usually see, at least in India, during monsoons, we see flooded. I mean, we see our areas getting flooded. So to answer these questions, okay, will my property flood or not? Or okay, if I have 100 millimeter of rainfall, so that comes under surface water flooding, which we also call it as pluvial flooding. And okay, so should I relocate my property if the water is, or if the river is out of the bank? So that is fluvial flooding. So we apply inflows to our rivers, and that is fluvial flooding. And yes, so tidal flooding is also self-explanatory. That will tsunami touch my plane if there is any case. So this is how this field is evolved, and that is how we answer questions by building models. Then yes, this can't be done by hand because the hydraulics or the mathematical equations are quite laborious. So that is why we build 1D, 2D, or 3D models, or in some cases we build linked 1D, 2D, or in some cases we build 3D models. And I think our second bullet point, which we have already discussed before, that is what are the sources of flooding. And after we do everything, so maps are produced based on various written periods, like depth maps, extent maps, water level maps. So people should know more. Okay, what if my property floods? Then okay, I'll have this much millimeters of depth. Okay, so what will be my water level, or what will be the extent? I mean, if we want to purchase any, should we purchase property if I'm at risk, or if that property is at risk? So these are the answers that are generated after building the flood models. Then solutions are nothing but mitigation measures. I mean, in your city, or if you look around, you would see that several levees or embankments are built. Then I think flood forecasting, everybody knows what it is. Then a few check dams are built for lift irrigation projects. So what will be the impact of it? Then SERTS is nothing but sustainable drainage management. Then what are the natural flood management options? Like, okay, can we improve infiltration so that by planting trees? So that's afforestation. So leaky dams in order to avoid flooding in our urban areas. Then even remeandering is also done as part of solution. So these are the mitigation measures that are done in flood modeling. So state of the art. So as I previously discussed, okay, so should I go with 1D? So you should really have a good understanding, or you should know your objective, or what you're trying to achieve. So you should answer these questions before starting any flood model. Okay, so should I build only 1D model? Should I go with 2D model? Okay, then what is the DTM? Because DTM picks only water level. So do we need survey? So okay, so is it necessary to build linked 1D or 2D models, that is river channel modeled in 1D, or and floodplain modeled in 2D? Then in some cases, we also have our stormwater network in place if we are talking about urban towns. Yes, so depending on these questions, you should develop your answers. Okay, so should I go with 1D, 2D? Based on my experience, we sometimes build 1D models, 2D models, and linked 1D, 2D models. And we rarely go with 3D models unless we want to achieve any accurate answers. Then yes, so there are various softwares in the market, like flood modeler, to flow. Then there's ICM. Then you guys should have known HICRAS, HMS. Then there's drains. So there are various softwares. So we should really understand what are the pros and cons of those software. Then we should also, I mean, we should have a better understanding. So in order to get that understanding, you should calibrate and validate your models. So what is this? So calibration is nothing but fixing your parameters and checking. Okay, I mean, we have various flow and level gauges. It is nothing but testing your parameters, so for any historical event, and using the same parameters you should test with another historical event. So for example, if I test my model with for example, if there was flood in 2012, so I'll test my model with that. Okay, I'll check, okay, are the results within the tolerable limit at that gauge? Okay, fine. Then I'll take that model, I'll just change my rainfall or whatever my inflow is, and I'll just check that for another event like 2016 if there was flood. So if these two things satisfy, then okay, I'm fine to go with it. So that is how I've answered my third question: is my model accurate? Then again, there are various GIS software. I mean, people I think know ArcMap and QGIS. So these are the two industry softwares that are used in the market. But other than that, you have MapInfo, ERDAS, as per my knowledge. So these are the state of the art technology that are used. Now, going to the case studies. So this is a dummy model which I had built. So on my left, you can see that this is, I mean, the colorful is the DTM or the ground model. Then I have inflows applied over here, which is nothing but a triangular hydrograph. So again, this is a dummy hydrograph, and these are my cross sections which I had extracted from the ground model. And this is my downstream boundary condition. So while building any model, people should be aware that I mean, there are five parameters or five boxes, I'll say. First is the general parameters. So what's the temperature, what is the specific gravity that you'll be using in the model. Then second box is your geometry. So geometry is equivalent to your DTM or your ground model, or what is the roughness. So that's geometry. Then upstream boundary condition, or even these cross sections can be classified into geometry because this falls under geometry. Then upstream boundary condition is my third box, and fourth box is my downstream boundary conditions, and fifth box is my initial condition. Because initial conditions are necessary because there will be some water, or there will be some existing water, or there will be some existing flow in it. So the initial conditions are required. So these are the five boxes while building any 1D, 2D, or 3D model. So I'll repeat that again. First is general, second is geometry, then third is upstream boundary condition, fourth is downstream boundary condition, and fifth is initial condition. So you should be aware of this five things while building a model. So yes, so this is my upstream boundary condition. Then red is my flow hydrograph extracted at first cross section, and I think this is green color which I've extracted at last cross section. So you can see, I mean, we normally study what is attenuation. So you can see our flood has attenuated. And yes, so this is the L section. So starting from first cross section to last cross section, let me just click on this. I'll be in the position to show you the animation. Okay, yes. So this is how my flood rises and it goes down. And that was my initial condition where it stopped. Or I mean, initial condition is nothing but this, but as I have my starting flow same as equivalent to ending flow, so we could say, okay, so that was my initial condition. So but initial condition is nothing but this, your starting point or at 0th time. So this is my 1D model case study, and I had built on the similar lines or with similar extent. So so this was built in 2-flow, and 2-flow requires code area which is in red. Then geometry is nothing but which comes from the ground model. So this is the colorful is the ground model. Then black line is my upstream boundary condition wherein I had applied flows. And this is my downstream boundary condition where I had applied my normal depth. Yes, so on my left, this is depth, and this is velocity. So I'll play this again. And this model was built in 2-flow, as I said, but this geometry or this polygons or polylines were generated in QGIS. So that was animation of depth, and this is animation of velocity. So you'll understand how the vectors or how my flow direction is. I mean, yes, the difference that we saw over here was that in my 1D case study, we didn't observe any flow going out of the bank. I mean, it was within the bank, but I had extended my cross sections at regular intervals along this periphery. But in 2D, so this is the advantage. So depending on your case study, you'll get this, okay, my water goes in then come back into the channel. So this is the beauty when we do 2D flood modeling. But depends, I mean, how big is your model? If I have my model big equivalent to 200 kilometers, then I'll rarely go with 2D, because the computation time it takes, then the cell sizes, I'll not touch that part much, but it takes long time to run the model. So we don't usually go with 2D, but we go with 1D. But if I, for example, if this is only my case study, then I could easily go to 2D. So that is why you can see 2D model. I mean, another dummy case study, 2D model, which I had developed. So these are, I mean, these were my two case studies. Then, okay. So career path. So what's required to do this? I mean, people ask me, okay, what is required? I mean, okay, civil engineering is fine, but is it civil engineering only? Because I have seen people in the UK who have done geography, or who have done their BScs or MScs in mathematics. So people can enter flood modeling even though if they have done geography, but at least civil engineering, geography, or environmental, or I don't know if there are colleges who offer water resources, but yes, bachelor's is required. Then masters. I am personally water resources and environmental engineer. So yes, I've done my water resources, but okay. Other than water resources, there are some colleges which offer this courses like hydraulics or marine engineering, coastal engineering. So yes, masters is required. Then so other than our Indian degrees, so there are also colleges or universities which offer MS or MSc courses in US, UK, and Australia. So you can do that. Then my best advice also is that you should know Python or machine learning or the artificial intelligence, then deep learning. So people should also have good knowledge about that. Or if you have done Python, then you can also enter flood modeling. And I think I've missed over here is you can also do remote sensing. I think one of the IITs or NITs offer this course, that is masters in remote sensing or GIS and remote sensing. So that is also one of the courses that can be done in masters, I think. Then PhD. And yes, so that is the career path that is how people can enter flood modeling, or they can do flood modeling. Then after you complete your education, so what are the job opportunities or entrepreneur opportunities? So we have at least in India, we have government organizations working in Central Water Power and Research Station, then CWC's Central Water Commission, and WAPCOS's Water and Power Consultancy. So these are the government organizations that I know, but I also know that there are few organizations which work or based on their state. Like there are various irrigation departments, place which do flood modeling. Then PWD's railways. I don't know how much they do in PWD or railways. I think they do based on empirical formulas, but at least I work for UK, so we do them for highways and railways. So there are various multinational companies like Jacobs, which I'm in. Then local consultants, insurance companies. Insurance companies usually do risk analysis, that is probability into consequence, that I said in one of my slide in the first bullet point. Okay, so there is less work done in India, so there is again ample of opportunities uh, to work in India. Then I think last week or 2 weeks ago, our Prime Minister announced that he'll be providing us with DTM freely available. So then even HECRAS and HKHMS are open source software. So you guys can take your project and do flood modeling. Then software development, if you are good with coding or your Python or any other C or C++ skills, so that is also another opportunity. Then construction and maintenance, like flood defenses, culverts, bridges. So these are mainly related to construction and NGOs. So yes, you can educate masses. Then blogs, you can write blogs. I usually write blogs, but I don't circulate it on LinkedIn, but they're only related to my I only circulate them in Jacobs. So these are the variety or ample of opportunities in flood modeling. So yes, that is it.